Welcome back to our machine design series. This is going to be our final topic before the final exam, and so I hope you're excited to wrap up this series with me. Now, today we are talking about the fatigue failure of fasteners, and a couple of notes just before we dive into it. When we have a bolted joint, and by the way, this is all going to be for tension-loaded bolted joints. There are modifications that you could make for shear joints that you can find in your textbook. For these types of joints, we can analyze them exactly the same as we did in Chapter 6. The methodology that we're going to use follows Chapter 6 exactly. We're just using the terminology and the variables that we've developed for fasteners particularly. Some other particular things for fasteners you can find in your textbook in a couple of tables. So table 8-16 has fatigue stress concentration factors for threads of different sizes, and table 8-17 has fully corrected endurance strengths for bolts and screws with rolled threads. When you're using values from table 8-17, you do not need to use a fatigue stress concentration factor from table 8-16 because it's already built in to that fully corrected endurance strength in table 8-17. When you have cut threads, instead of using table 8-17, you just use methods directly from Chapter 6. And keep in mind that the endurance strength for fasteners with cut threads will be considerably lower than those with rolled threads, as is in table 8-17. Remember that for rolled threads, we get a lot of cold work, strain strengthening, and so that leads to higher endurance limits for rolled threads. Okay, so with that out of the way, let's define our maximum and minimum forces in the bolt using the preload and the maximum and minimum external load applied. Now, these are the maximum and minimum fluctuating forces that will be felt by the bolt, and we can use that to develop equations for the alternating stress and mean stress in the bolt. And remember, that's what we use in Chapter 6 to develop fatigue safety factors with Goodman criteria and other fatigue criteria that we developed back then. Okay, so this is just taking our same equation we've used for alternating stress before, our maximum and minimum stress, divide them by 2, and we've just taken the maximum minimum force and then divided by 2 times the area, because remember, force over area gives us tensile stress. And I realized I didn't go over what all of these variables are, so just to make sure that we're on the same page, this is our tensile stress area in the bolt, which you can look up in a table in your textbook. Okay, you can find this in table 8-1 or 8-2, depending on if you have metric threads or US customary system threads. Other variables here that we've already used up here, so we used this joint stiffness constant. So remember that this is the ratio of the stiffness of the bolt to the sum of the stiffness of the bolt and the members that are being clamped. And then, of course, Pmin, Pmax, those are the minimum and maximum external load. Okay, so now I'm just going to plug in these expressions that we have up here for FBmin and FBmax into this equation. And we can simplify this. We can get rid of both of these FIs, they cancel. Okay, there's our alternating stress. Now let's do the same thing for our mean stress or our mid-range stress. Okay, something important to note before we move on here too is that because we're using this tensile stress area in all of these equations to calculate the stress in the bolt, that means that we're looking at the stress in the threaded portion of the bolt. And normally that is a very reasonable thing to do. In the Peterson Stress Concentration Factors book, there's an observation that typical bolt failures will happen about 15% of the time under the head of the bolt, 20% of the time at the first fully formed thread, and 65% of the time at the first fully engaged thread in the nut. And so for the most part, we would expect to see failure, if it's going to occur in a fastener, in the threaded portion of the fastener. And so that's why we use the tensile stress area here. But if for some reason you want to calculate the stresses in the smooth shank portion of your threaded fastener, then you would not use the tensile stress area here. Instead, you would use that cross-sectional area of the diameter of the bolt. All right, so now let's write out our fatigue factor of safety, and I'm going to do that using the Goodman line. There's a derivation in your textbook if you'd like to look at it, but I'm just going to skip to the good part and give you the fatigue factor of safety, and that'll be on your equation sheet when you're taking the final exam as well. All right, here's our equation for the fatigue factor of safety using the Goodman criteria. Keep in mind again that this endurance limit, this is a fully corrected endurance limit, which you can find in table 8-17 for bolts with rolled threads. SUT, this is our ultimate tensile strength, which you can find in tables 8-9, 8-10, and 8-11 in your textbook. And then what else do we have? The alternating stress and the mean stress, which we just calculated. And finally, this is our preload stress. So that's the preload force divided by the tensile stress area. So let's do a quick example and then we will wrap up this video. All right, here we go. So we have an M20 by 1.5 by 63.5 millimeter class 8.8 bolt. We have a fluctuating load that reaches a maximum of 26.69 kilonewtons, goes down to a minimum of 0. We have a preload of 111.205 kilonewtons, and we're given the stiffness of the bolt and the members. The bolt is 1.14 meganewtons per millimeter, and the members have a stiffness of 2.42 meganewtons per millimeter. And we're simply asked to find all factors of safety for this joint and explain what they mean. Okay, and one more thing I almost forgot. This is a non-permanent installation of this bolt. All right. So with all of this information, let's get started. First thing we want to do is determine our preload and our service load stresses in the bolt. And then we're going to compare that to the proof strength when we find our factors of safety. So our preload stress is simply equal to our preload force divided by the tensile stress area. You can find this tensile stress area in table 8-1. And when I look up that value for this M20 bolt, I find that it is 240.645 millimeters squared. Now don't forget to multiply this top line by 1,000 to get newtons per millimeter squared. And those are consistent units that will give you megapascals. If you don't believe me, I encourage you to go ahead and try it, prove it to yourself. And the number you should get out of here is 462.1 megapascal. That is our preload stress in the bolt. Next, to be able to find the stress in our bolt due to the external load, we need to find our joint constant, because that tells us the portion of the external load that goes to the bolt as compared to the portion that goes to the members. So our joint stiffness constant is equal to the stiffness of the bolt divided by the stiffness of the bolt plus the stiffness of the members. So that's going to be 1.14 over 1.14 plus 2.42. This is going to give us a unitless number, so I've dropped the units. As long as they're consistent, that's fine. And it gives me 0.32. Okay, so now let's find the stress in the bolt. And let's find the maximum stress in the bolt. The minimum stress in the bolt, of course, is just the preload, because the minimum external load is 0. So when we have 0 external load, we're still going to have this preload stress in our bolt, and when we have an external load, we're going to have this preload stress plus the portion of the external load that goes to the bolt, which we determine from C. So it's going to be FB max over the tensile stress area, which is C times P max plus preload over the tensile stress area. This is a slightly different way to get to the alternating and mean stresses is what I showed before, but I want to find the maximum stress so that I can find my static factors of safety. Let's simplify this a little bit. Just to make our lives easier, we can say that this is C times P max over the tensile stress area plus sigma I. I'm doing that because I already know what sigma I is. So now when I plug things in, I get 0.32 times the maximum external load, which was 26.69, and I'm going to go ahead and convert that to 26,690 newtons, divided by tensile stress area, which is the same as it was before, 240.645 millimeters squared, and then add our preload stress, which is 462.1 megapascal. And when you add all that up, you should get 497.66 megapascal. To find our factors of safety, we need to know what the proof load is of this bolt. And we can find that in table 8-11 in the textbook. For this class 8.8 bolt, we have a proof stress or proof strength of 600 megapascal. So now let's compare that to the stress that we got to work out what our factors of safety are. For the yielding factor of safety, just comparing the stress in the bolt at maximum to the proof strength, we can find our first factor of safety, which is NP equals our proof strength over the maximum stress in the bolt. So that's going to be 600 over 497.66, which is 1.21, or let's just say 1.2. But remember, when we developed this equation in our last video, we said that this is often not much greater than 1, and that's what we see here. This is our traditional factor of safety, compares our maximum bolt stress to the proof strength. But now let's look at the load factor. Okay, and for the load factor, we got a much higher number. We got 3.9. And what this factor of safety means is that we can apply 3.9 times the external load without exceeding the proof strength of the bolt. So this is really just an indication of the overload on P that we can withstand. Okay, now we have one more static factor of safety to calculate, and that is the opening factor of safety. So this factor of safety just tells us at what point the joint will separate. So if our force, our external load gets too large, the joint is going to separate and the bolt will take the entire load. In many cases, we would consider that a failure of the joint. And so this factor of safety tells us how far away we are from that event. All right, now we're ready to calculate our fatigue factor of safety. So for fatigue, we are going to need our alternating stress and our mean stress. We already have our preload stress, so we can use that to calculate the mean and alternating. All right, so our alternating stress is just going to be the maximum minus the minimum, which in this case is our preload, divided by 2, and that gives us 17.78 megapascal. And then our mean stress is our alternating stress plus preload. And just as a quick reminder, remember that our mean stress is, of course, the mean value of stress in our stress over time plot. So this is not going to be drawn to scale, but for a scenario like the one we have this alternating stress. Our minimum value is our preload. That's the load on the bolt at time 0 before we start applying our additional external load. And then we reach a maximum stress of the sigma B max, which we've calculated already. And remember, that is the stress due to the preload plus the portion of the external load that is going to the bolt. And our mean stress is this halfway point. And then, of course, our alternating stress is the amplitude of this wave. Now that that's taken care of, let's calculate our fatigue safety factor. And I'm just gonna scroll up and go grab the equation and bring it down so that I don't make any errors. Okay, now you'll notice that in this equation we have a couple of things that we need that we don't already have. The first one is the endurance limit, which you can find in table 8-17 in your textbook. And so yes, that means that we are assuming that this fastener has rolled threads. And when we look for the endurance limit there, we find that it is 129 megapascal. And if you didn't know whether the fastener had rolled threads or not, when you do your analysis, you should make some kind of note to make sure you note that you've assumed you have rolled threads, and then you can go back and validate that assumption later on. The other term that we don't yet have is the ultimate tensile strength, which can be found in table 8-11 for this bolt. And it is 830 megapascal. And that's for a class 8.8 bolt, which is the specification that we had. So now, yeah, I think we're ready to go. We have everything we need. Let's plug into our equation and solve for the fatigue factor of safety. Okay, so we find that our fatigue factor of safety is 2.8. And again, remember that this is the fatigue factor of safety using the Goodman criteria. And if you're interested in what assumptions are built into that, I encourage you to go check out that section in chapter 6 of your textbook. So now let's take a look at an overview of these three safety factors. So we have 2.8 for our fatigue factor of safety guarding against fatigue, 6.1 for separation of the joint, 3.9 for our load factor, and our yield factor of safety is 1.2. So while this factor of safety guarding against yielding, this traditional factor of safety guarding against yielding is low, we would probably in this scenario consider fatigue to be the greatest threat to failure of this bolt. And that's because we know that this factor of safety, this traditional factor of safety is going to be low, it's going to be close to 1, and that's just because we load bolts in tension. We apply a significant amount of preload to bolts to strengthen the connection. We have another factor of safety that indicates whether we can apply more load to the joint or not, and that factor of safety tells us that we have 3.9 times the external load that could be applied without exceeding our proof load. So when we think about it that way, then it does appear that our greatest threat to safety of this joint is going to come from the fatigue factor of safety. But all factors of safety are over 1, and so this design we don't predict failure of the design. All right, so with that, I hope that you found this video useful. We looked at all the factors of safety that you could calculate when analyzing a bolted joint, both fatigue and static factors of safety, and talked about what they mean. And then earlier in the video, we of course developed the fatigue factor of safety, looked at equations for alternating and mean stress in the bolt using terminology and variables for bolted joints specifically, and talked about a few exceptions to the rules when it comes to fatigue failure of fasteners as compared to the fatigue failures that we talked about in chapter 6. So with that, I just thank you for watching, and I hope to see you in the next one.